Welcome to this lecture where we're going to talk about tree rotations for AVL balancing. In this lecture, we'll talk about the two different types of imbalances that can occur in AVL trees, and we'll talk about fixing those imbalances with what are called rotations, and then we'll also talk about how to determine which kind of rotation is needed. So, when a tree becomes imbalanced, um, uh, it becomes imbalanced because we break this AVL balancing rule. The AVL balancing rule is every sibling pair has a height difference of at most 1. And inserting and removing from an AVL tree can cause two kinds of imbalance. The two kinds are listed here, and there are also mirror image cases. And when I say mirror image, you can imagine sort of flipping this image and the values around, or this image and its values around, so that we have this mirror image case. But we'll just draw the two cases and leave the mirror images for you to work out on your own. So if we had a tree which looks like this, and if before this tree was AVL balanced, it looked like this, and then we inserted 6, okay? So this tree is the previous tree, it's AVL balanced, and you can check that. And then if we insert a 6 right here, then it becomes imbalanced, and the place where it becomes imbalanced is at this node. Similarly, if this tree was like this and it was balanced, we insert the 8 right here, the tree becomes imbalanced right here. Now let's look at why this imbalance occurs. This has a height of 0, this has a height of -1, right, this null node. This has a height of -1, and this has a height of 1. So the imbalance is between these two siblings, which means that we think about the imbalance as being this node as being the parent of that imbalance. So we focus on this node 9 as having the imbalance, even though it's really its children. And similarly, we have a null node with a height of -1, 0, 1, and -1, and we can see that there's an imbalance between these two nodes, which we signify with that node. Okay, so the imbalances could have happened due to these insertions that we're talking about. If I insert 6 here, or if I insert 8 here, these cause these imbalances at the same node, 9, but these are two different cases and we handle them in two different ways. This one is the left-left case, and the mirror image would be the right-right case. The right-right case, of course, is just if you took this and flipped it horizontally, you would get the right-right case. And this case is the left-right case that you see here because it's left and right. And there's also a mirror image, which you can imagine, which is right-left. Okay, so we need to be able to fix these imbalances as soon as they occur. So if we did an insertion, we need to be able to fix that. It's quite simple, at least conceptually, to fix the left-left imbalance. What we do is we do what's known as a single rotation to the right, or a right single rotation at the imbalanced node. Here the imbalanced node is 9. So what we're talking about here is what's known as a tree rotation. And a tree rotation, you can think of it as, I like to think of it as there's a pulley right here at the node where we're doing the rotation. And the nodes are going to sort of rotate around that pulley in the direction that we're talking about. So this is a right single rotation. So the nodes are going to move to the right around this pivot point or this pulley point. So what does that mean? That means that 9 is going to come down, 7 is going to come up and take its place. Okay, and that's what we see over here. Notice 9 has come down, 7 has taken its place, and 6 retains the same relationship with 7 that it had before. So nothing has changed here. This link hasn't changed. Okay. This is a single right rotation at 9. That's what this would look like. A single right rotation at 9 gives us this. And you can see now, this is now a balanced tree because we have height 0, 0, 1, and we have height 0, 0, 1, 2. And so the sibling height difference is at most 1 everywhere. Okay. So the left-left imbalance is fixed with a single right rotation or a right single rotation. The mirror image of a right-right imbalance, of course, would be fixed with a left single rotation in a similar fashion. Here is the general idea behind a right single rotation, not for a specific example necessarily, but for, sort of a more generic idea of maybe a rotation in the middle of a much larger tree. If we have that we want to do the rotation to the right at 30, so we're thinking about a right rotation that goes like this at node 30. 30 is going to be demoted, 20 is promoted into its place, and there's one extra piece of information that we have to keep track of. What's going to happen to B? Well, 30 becomes the child of 20, as you can see here. So B has to become the child of 30. So the things that change here are the left child of 30 rather. This node, or this pointer, is going to now point to B. The right child of 20 is now going to point to 30. And there's also one other change. The parent of 30 was pointing to 30, now it has to point to 20. Okay, so those are the three steps that we make here. The rotated node, which is here 30, moves to the right. Its left child, which is 20, takes its place, and the right child of the left, that's B, changes parents. Okay, so most of the tree keeps its structure when this happens. The only nodes that change, really the only links that change, are this link, and this link. Now, because only 3 links are changing, this is an order 1 or constant time operation. So doing a single right rotation requires only constant time. The only 3 pointers are involved. And if we were talking, this is for a single right rotation, a single left rotation is just the mirror image of all of this. One last thing that I should emphasize in all of this is that when I said the tree keeps its structure, notice that if you did an in-order traversal of this tree before and after, it would be A20, B30, C50D. And still you have A20, B30, C50D. So a rotation doesn't reorder the nodes, it just re-ranks them hierarchically. Now, the second case that we talked about was the left-right imbalance. To fix a left-right imbalance like we have here, we have to do what's called a double rotation at the imbalanced node. And a double rotation is sort of what it sounds like. It is 2 single rotations. So look, a double rotation, in this case, a left-right double rotation, starts here and does a left rotation at 7. And when we do the left rotation at 7, 8 comes up and takes its place, and 7 goes down. Okay, now we have this situation. Okay, this is after the left rotation at 7, which was previously here. Notice that this situation looks strikingly similar to the situation of the left-left imbalance that we had before, for which we needed a single right rotation. And that's what we do. We do a right rotation at 9, and we arrive at this situation. Okay, so the left-right imbalance can be fixed with a left-right double rotation at the imbalance node. And when we say at the imbalance node, you might notice that we actually did the first rotation at 7, not at 9, which is the imbalance node. Well, because a double rotation always proceeds in 2 steps, 2 single rotations, and the first one occurs at the child of the node where we're doing the rotation, in other words, the child of 9, and the second one occurs at the node of where the imbalance occurs. So here's the general idea for a left-right double rotation. If we're doing a left-right double rotation at 30, the process is we first do a left rotation at 10, and then we do a right rotation at 30. And the place where we end up looks like this. And again, all of these nodes retain their order. So the in-order traversal is A10, B20, C30, D, and so on. And if we look over here, it's still A10, B20, C30, D. So nothing has been reordered, we've just restructured the tree. So a double rotation is just 2 single rotations. They occur in opposite directions, so it's always left-right or right-left. And they occur at different nodes, and always the deeper one first, and then the shallower one later. The deeper one is the child of the node at which we're thinking about where the rotation originates, where the imbalance occurs, right? The child of 30 is where the first rotation occurs, And then at the node where the imbalance occurs is where the second rotation occurs. Now, because this is two single rotations, and each single rotation is a constant time operation, that's just two constant time operations. So overall, this is a constant time operation as well. And again, the mirror image of this is a right-left double rotation, which we could show as well, but we're not going to for here. The last thing to talk about is how do we figure out which rotation we need to use? How can I tell which situation am I in? Am I in the left-left or right-right, which are essentially the same, just mirror images, or am I in the left-right or right-left? Okay, how do I tell the difference between these two cases? Really, it's four cases, but it's two classes of cases. Well, here's the way that you should think about it, and I would suggest that you think very carefully about how this works, okay? Because the details here are pretty important. Let's suppose that n is the imbalance node. So here n is either this node or this node in pink, okay? And let's suppose that it has height h plus 2 for our example, whatever h is, okay? Then here's the important part. Let C be the taller child of n, which has height h plus 1. So C is the taller child. I don't care, it could be the left, it could be the right, but it's the taller child. And I know that if it has height h plus 1, and it's the taller child, that must be the reason that n has height h plus 2. Because n, in computing its height, must take the taller of its children and add a 1 and get its own height, okay? Now, you notice that there is an imbalance here because C, which is the taller child, has height h plus 1. Its sibling, which is an entire subtree, this represents an entire subtree here, has height h minus 1. So that's a difference of more than 1. So this is not AVL balanced. Okay, so we go from n to the taller child, and then from there we go to its taller child, which in this diagram is here, and this diagram is here. Okay, so we go from the node where the imbalance occurs to the taller child to the taller grandchild. Okay, and that taller grandchild has height h, and we're calling it g. Okay, so this is, we've detected an imbalance at node n, which is really the sibling or the children of node n. Then we've gone to the taller of its two children. And then we've gone to the taller of that node's two children. That structure forms a pattern. So if we look at n, the path from n to c to g, if those are in the same direction, in other words, here we have left left, we might also have right right, okay, in a mirror image. If those are in the same direction, we use a single rotation, and that's a left or right single rotation. And in this case, we would want a right single rotation since we're taller on the left and the left, okay? So if n to c to g are in the same direction, use a single rotation. If n to c to g switch directions, if they switch directions, use a double rotation, which is either left right or right left. And in this case, we would want a left right double rotation to fix that imbalance at that node n. Okay, so these are the rules for how to apply which rotation, or determine which rotation we need before you apply the rotation that you need. Now there is one tiebreaker. If you're paying very close attention, it could possibly be that when you go from the node where the imbalance occurs to its taller child, those two nodes cannot have the same height, because if they did, there would be no imbalance. So if we go to the taller child, and then we go to its taller child, okay? In this diagram, I've drawn it such that these two have different heights and these two have different heights. But it is possible, under certain circumstances, that these two have the same height, okay? And that can only happen on remove. If that happens, in other words, if you're unable to determine whether this is a left-left or left-right because these two have the same height, then the tiebreaker is to use a single rotation, and that is also important, okay? So the pattern is, look at the node where the imbalance occurs, look at its taller child, look at its taller grandchild. If those are in the same direction, use a single rotation. If those are in different directions, use a double rotation. And if there's a tiebreaker that we need because the two grandchildren of the child, the taller child, are the same height, then use a single rotation.